Okay, so yesterday we were talking about this this topic, right? The independence of n random variables. I thought it's a good time to be a little more formal about it, or go a little more into depth on the in this. So what I'm asking you to do is consider n trials of some experiment and define the random variable xi only for the ith trial, right? You in other words, I do not want this xi to be defined as the sum of all the numerical observations that you may make from different trials or anything of that sort, right? Each trial is associated with one random variable. If you toss a die n times, the natural thing to say will be the right, xi will be the outcome on the ith trial, for example, right? But so I want to define xi only for the ith trial, so therefore I have defined xi all the way from I equal to 1 to n, right? So these n random variables, they actually turns out that they satisfy a very interesting property in that because the trials are independent. When I say n trials, automatically the n trials are independent, right? So the events x1, if you look at these events, now you might ask the question, why do we repeat the x? This x1 is just for notation. I could have written a, b, c, d up to n if I wanted, right? But that way I don't get enough a, b, c. So it's the normal thing to do is index these things also, and just to keep the confusion as small as possible, whatever you repeat the x, but write it as lowercase x here for the values that they take, right? That's what we've always been doing. So we have these events x2 equal to x2. So these n events, these are all independent. For what choice of vector small x, for any vector, for every, right, useful or every useful, what I'll have to say what I mean by useful, choice of x1, x2, xn. So you have an n vector that you're going to look at. What do I mean again by useful? This joint probability has to be positive. I don't want this joint probability to be 0. This is a joint probability that I want to choose a small xi's such that this joint probability is positive, and we have that quantity being equal to the pi product of xi, the individual product of the probabilities of the individual events, right? Remember I said xi is based only on the ith trial, so this small xi is a number which comes out only of the ith trial and nothing else. Not only this, right, so and what do we mean by n events being independent? This is obviously not the only condition, right? We have to have this condition being satisfied for any subcollection, which is also true, because when you have n trials, you can obviously close your eyes to the trials you don't want, right? So a similar statement or equivalent statement holds for any subcollection. of the n trials. So, I mean, all of this follows just from the n independent trials, right. If you have n independent trials, you can always disregard some or as many of them as you want to disregard. You can focus your attention only on what you want to look at. So, if I want to look at only the first 3, then I have these just the 3 and I get the product of the first 3 things. And the small xi, remember again, for every useful such vector where the joint probability is positive. So, in the case of die rolling, I should be able to substitute in the place of small xi. If I said that xi is the ith number, I should be able to substitute any number from 1 to 6 out here, and this joint probability will be equal to this product of these individual probabilities, right. So, when this happens, you say that, so this is a very important special case of having n independent random variables. So, the collection, you say that the collection xi I equal to 1 to n is independent. So, which means that any subcollection of this is also independent, and so is any subcollection. So, here we are looking at all n of them. We can also look at so, right, the English word so used to refer, copy this property onto any subcollection. So, this is a very, very important concept because it allows us to mathematically bring in this repeated trials, put a mathematical face on the repeated trial and say, okay, you can define random variables for each trial. Note that we do not have to straight away assume that the xi's must have the same distribution. For example, I can say on the first trial I am taking the number itself, the second trial I am going to take the square root of the number, the third trial I am going to take the third root of the number, so on and so forth. I need not have the same xi, I mean the same definition for how do I measure the the random variable. It could be different on each trial, but in the most useful case, you have exactly the same way of obtaining the xi, the same way of defining the capital Xi, the random variable itself, as the number that comes out. So, therefore, in most cases the xi's will have the same PMF, right. So, first we understand that they are independent, then when the xi's have the same PMF, what do you get? You get IID. The collection is independent and identically distributed. So, this is, again I stress, this is an extremely important and useful concept and we will use it a lot when we look at asymptotic behaviors like the law of large numbers and things of that sort. So, I can, what I am trying to say is I do not have to go through all this song and dance each time, right, to justify talking about NIID random variables, that is all. I can just straight away start with that. Let me start with a collection of NIID random variables. Immediately I can go to that. Alright, so now let us continue with the 2 random variable case, back to the 2 random variable x and y, back to independent x, just 2 random variable. If you have just the 2 random variables, you know, so this means that the the joint is a product of the marginals. So that also means that the conditional densities, or conditional PMFs, P of y given x for example, will be what? Just the unconditional, the marginal PMF for all values taken by x. That is, no matter what value you use for the conditioning quantity, you get back the same unconditional PMF. In general, remember, as we saw in the trinomial case, if you put different values for x, you get different PMFs. In the trinomial case, please go and look at it more carefully, right? For each value of x equal to I, the PMF was different, it was not the same. But when they are independent, you not only get the same value, same PMF for every value of the conditioning x, and it's also equal to the unconditional PMF itself. So in other words, well and truly, observing x tells you absolutely nothing about y, and vice versa. Since they are functions, I am just writing this is a functional equality in some sense, right? The whole entire mass function is the same. So omega x in this case, the omega y will be unchanged also. Observing x does not tell you, does not increase or decrease omega y in any way, it keeps it unchanged. You get no change at all in the situation as far as y is concerned. Similarly here, if you observe y, you get no information about x. So both, if x and y are independent, both of these will hold, obviously, right? So it's more than just simply writing joint as a product of marginals. It's a lot more going on that we have to be aware of. Okay. Clearly, the dependent case. What is the opposite of independent? Dependent, right? So let me just say, right? If it when x and y are the trinomial case, for example, are, remember, they are dependent. With a stress on the word, on the syllable D, right? Independent versus dependent, right? So independent random variables are more difficult in the sense of being more mathematically complicated, because the joint PMF is not obtainable from the marginals in the dependent case. You have to do a lot more work to either get it numerically or model it mathematically. You can't just simply close your eyes and multiply the marginals and say, okay, this is the joint. Not only that, the random variables that you associate with sampling without replacement, they are typically dependent. The first trial you get something, then you throw that away, you don't add it back to the mix, then you take out a second one. Unless the whatever you are taking off is so big that the taking out the first one doesn't statistically change what is happening there, right? In general, sampling without replacement gives you dependent random variables, not independent. Like for example, the other case that we studied, right, of drawing two numbers from 1 to n. So sampling without replacement, right? So it gives you dependent. So we can always shrink independent to INDEP and dependent to DEP. Of course, IID is another very important acronym we will be using a lot.